In this video, we are going to do another example of finding local maxes, local mins, and saddle points of a multivariable function. So I want to begin this by giving you the chance to try this question. That's really important with these types of problems, getting practice with it, because it combines so many concepts. So pause it for 4 minutes this time, because these are longer. It's probably not going to be enough time to finish the question. I mostly want you to think about what are the key steps and getting started with that. So 4, 3, 2, 1, pause that video. Pause it for 4 minutes to try this question. All right, so hopefully you did that. Hopefully you paused it for about 4 minutes to really try this question. So let's talk about the solution. So what I need to do first is take my partial derivatives and set them equal to 0. So I'll take the partial with respect to x, set it equal to 0, and the partial with respect to y, and set that equal to 0. So let's take those partials. So the partial with respect to x, at this point I'm going to start to speed up my process a little bit of taking these partials, because we've done a number of examples now. So for the partial with respect to x, for the first term I'll get negative 3x. For the next term I'll get plus y squared. And then for the last term, I'll get 0, because it gets treated as a constant. There's no x's in it. And I set that equal to 0. Partial with respect to y now. The first term derivative would be 0. The next term derivative would be 2xy. And the last term would be minus 32 over 3 times y. And I set that equal to 0. All right, so now I have this system of equations, and I'll continue this on the next page. All right, so we have this system of equations. I could technically work with either one of these equations, but I noticed that with the second equation, I can factor it, so I'm going to choose to work with that one. But I could also work with the first one first if I wanted to. So in the second equation, I noticed that they both have y in common, so if I factor that out, I'm left with 2x minus 32 over 3 equals 0. And now that this is factored and it equals 0, either that y at the front is going to be equal to 0, or the second factor, 2x minus 32 over 3, is equal to 0. So let's solve this equation. So I get 2x equals positive 32 over 3. And then if I divide by 2, we get x equals 16 over 3. So we have these two possibilities, either y is 0 or x is 16 over 3. That's what we got from the second equation. So let's take these and plug them into the first equation. So if y equals 0, then when I plug it into the first equation, negative 3x plus y squared equals 0, that implies, so that arrow just means implies, that implies that negative 3x plus 0 equals 0. And if I divide by negative 3, we get x equals 0. All right, let's do the same thing for the other point. So now if x is equal to 16 over 3, then from the first equation, negative 3x plus y squared equals 0, plugging into that, that implies we'll get negative 3 times 16 over 3 plus y squared equals 0. And I can simplify this. I'm actually going to write the y squared term first, because the 3's cancel, and I'll end up with a minus 16 equals 0. So there's a few ways to solve this. One way is the left-hand side factors. It's a difference of squares. So it factors as y minus 4 times y plus 4 equals 0. So I get from the first factor y equals 4, and from the second factor we get negative 4. So I could have also solved this equation by just moving the 16 over. So I get y squared equals 16, and then square rooting both sides. That would have given me y equals 4, but when I square root both sides, I got to put a plus or minus. So we would have gotten plus or minus 4. So I could have solved it in that way as well. All right. So we had plugged in y equals 0 and 16 over 3 into the first equation. Into this first equation. It's a good idea for you to just verify that they also satisfy the second one. So check. Turns out that they all do. Check that these satisfy equation 2. It turns out they do. So I'm just going to put this in a little bubble and leave that for you to just convince yourself that they do satisfy that second equation. If some of these points had not satisfied the second equation, then they would be extraneous. The points have to satisfy both of the equations to actually be critical points. All right, so we are ready to write down our critical points. So our critical points. So the one that we had first was x was 0 and y was 0. And the one we had second, well, when x is 16 over 3, there were two possibilities. Y could be 4 or y could be negative 4. So overall, we are getting 3 critical points. All right, so next we are ready for the Hessian. All right, so we are ready to compute h. So recall what our partials were. The partial with respect to x was negative 3x plus y squared. And the partial with respect to y was 2xy minus 32 over 3y. All right, so I'm going to need to know fxx, fyy, and fxy. For fxx, I look at fx and do the partial of that with respect to x, which is going to be negative 3. For fyy, I look at fy and do the partial one more time, but now with respect to y. So for the first term, that will give me 2x. For the next term, I will get minus 32 over 3. And for fxy, technically the order means do fx first, and then do the partial with respect to y. So if I look at fx, and now I do the partial with respect to y, we will get 2y. But by Clause's theorem, it shouldn't matter the order that I do these in. Even if I had done the y partial first, and then the x partial second, I would have gotten the same thing. Alrighty, so we are ready now to write down h. So h, recall, is fxx times fyy minus fxy squared. So if we plug into this, we get h equals fxx is negative 3, fyy is 2x minus 32 over 3, and then minus 2y squared. So if I distribute and simplify, we get h equals negative 6x plus, the 3's will cancel and I'll get 32, and then minus 4y squared. All right, so next let's make a table to classify these. Okay, so I've got it written in, but let's just move this up. So our critical points are 0, 0, 16 over 3 comma 4, and 16 over 3 comma negative 4. So in the table, I'm keeping track of my critical points, the value of h, the value of fxx, and then what my conclusion is going to be. So if I plug in 0 for the x and 0 for the y, I'm going to get that h is 32. So when h is positive like this, I need to know what fxx is. So in fact, if we flip it back to our second derivative test, this is either case 1 or case 2. H is greater than 0, it's positive. So I need to know if fxx is positive or if it's negative. That's going to tell me if I have a min or a local max. All right, and then fxx is negative 3. And when fxx is negative here, we are going to get a local max. In fact, if I flip it back to my second derivative test, this was case 2. The h is positive, but fxx is negative, so we have a local max. All right, let's go back to our table. All right, if I plug in 16 over 3 for x now, and 4 for y, I'm just going to do this on the side, we would end up getting negative 6 times 16 over 3 plus 32 minus 4 times 4 squared. And if I simplify this, the 6 and the 3 cancel a little bit. I'll be left with a 1 here, a 2 here. So negative 2 times 16 is negative 32. And then plus this other 32. And then I'll get minus 4 times 16, which is minus 64. So overall, this is negative 64. So h is negative 64. And when h is negative, we do not need to know fxx. We actually know the conclusion already. What case is this? H is negative. That is case 3. H is negative, so we have a saddle point. So let's flip it back to our table. All right, so saddle point here. And it turns out that when we plug in 16 over 3 for x and then negative 4 for y, we get the same thing as when we plugged in the critical point above. Because the only difference is the y value is negative, but when you square it for the y squared term, we're going to get the same thing out. So we'll get the same h value here, negative 64, which means fxx is not needed. Not needed, and then as in the previous critical point, we have a saddle point because h is negative. All right, so we are ready to write our conclusion. So by the second derivative test, this function, so our function was g here. It was g and not f. And actually, so now that I remind myself it was g, all of these f's that I had written down before, all of these should be g. So I'm going to fix a couple of these with you, and the others I'm just going to quickly fix. So this would be g of x, this would be g of y. All of these other f's I need to fix as well. I'm just going to quickly do that. All right, so I just quickly change all of those f's to g's. Okay, because my function was g here. All right, so by the second derivative test, our function g, whoops, this one should be g as well. Gxx, g has saddle points at 16 over 3 comma 4. Oops, let's erase that comma. And 16 over 3 comma negative 4. And a local max at 0, 0. And that is our answer.